All right, well, first of all, thanks for being here. My name is Rob Jackson. I'm a professor in the Department of Earth System Science, and I also have appointments in the Precourt Institute for Energy, as well as the Woods Institute for the Environment. So you can think of me as an environment person. The research in my group is split between sort of traditional ecology. I do global change research, drought-related research, forest mortality, and issues like that. But increasingly over the last 6-7 years, I've done a lot of work directly related to energy infrastructure. What are the environmental implications and benefits of different policies? How do we know what we know about climate change and water resources and issues like that? So that's sort of what I do for about half the time, what we do for half the time in my lab. And one of the things we've worked on a lot over the past 5 or 6 years is unconventional natural gas and oil extraction. So what you're looking at here is a picture I took from a helicopter. This is a site in the Marcellus while a hydraulic fracturing operation is going on. So you're looking down on that operation. You see the tanks there. You see generators, mixers. And then, of course, you see in the upper left corner a house. So I want you to think about how your view of this operation might differ depending on your relationship to what's going on outside your door. So do you, for instance, own the mineral rights for the activities that's taking place, in some cases, just a couple hundred feet from your house? Were the mineral rights to your property severed so that they're owned by someone else now, so that you, in a sense, get the bother of this activity without necessarily the economic benefits that come with that activity? So I think those kinds of questions explain some of the controversies that you read about and hear about associated with hydraulic fracturing. How many of you have seen hydraulic fracturing operation while it's been going on? Where were you? What's that? Texas, in the Barnett, the Eagle Ford. Okay, how about you?
Eagle Ford and Permian.
Eagle Ford and Permian, okay. Anybody else? One more? You are? Okay. All right, so we're going to explore just a few examples today, and the example that I'll focus on first and foremost are air issues, leaks from oil and gas operations. So what are people worried about or concerned about with these kinds of unconventional oil and gas extraction processes? Well, these are some of the things. Air quality interactions we'll touch on a bit today. Our group's worked a lot on water issues. I'll talk about that a bit as well. So you can think of grouping those into the water that's required to get the oil and gas out of the ground, the millions of gallons you hear about per well. The potential interactions with drinking water quality. Do these operations leak? Have they, and where, under what conditions do they impact drinking water for the 40 or 50 million people who rely on private water wells instead of municipal water sources that are protected? So no one tests the private water wells in the US unless the homeowner pays for those tests or associated with pre-drilling activities. The disposal of the trillion or so gallons of produced water, of wastewater that we generate each year from oil and gas activities. Where does that go? How do we keep track of it? How do we make sure that that doesn't end up in surface waters? And then other issues that you've heard a bit about or will this week, induced seismicity that people like Mark Zobak works on campus. And that's primarily associated with the disposal of wastewater, not just from oil and gas activities, but from anything else we do. And land disturbance issues, the well pads, the roads, the pipelines. Under what conditions are their effects on wildlife and other species important? So I'll just touch on water as I have very briefly. This is just a sort of a cartoon, if you will, of different places where you might think about water interactions. So you have streams and rivers nearby or ponds nearby that might provide the water that's used to hydraulically fracture that well. Or in turn, under worst case scenario, might be the place in which a spill from a site ends up. You have near surface activities and well integrity. So our group also did the first studies examining the potential for water contamination associated with hydraulic fracturing. We did these studies in the Marcellus originally, but have now done them in other places as well, in Arkansas and Texas and elsewhere. And a summary, I would have to say, would be that hydraulic fracturing can be and is often done well and safely. It isn't always done well and safely. And well integrity, the safeguarding the well in these shallow layers and these surface layers is key to that process. And then finally, the wastewater disposal we've touched on as well. Different states do different things. And that's one of the interesting things you'll study about here. Some states deep inject all of their wastewater. They pump it back deep underground. which has the issues associated with that, but keeps that water from interacting with the surface, ponds and rivers and such. Other states treat it or release it into systems after treat it. Other states recycle that water. So there's a whole group of activities. So water is really important. We don't have a long time today, so I want to hone in on air issues, just with a couple of research examples for you over the last month or two that we've done in my group. Now, first of all, some air benefits, some air quality benefits of natural gas compared to coal. Right? So natural gas compared to coal, and when it's burned, releases 90% less sulfur dioxide and mercury, less NOx, less particulates. These are things that can kill people and kill thousands of people still today in the U.S. from particulate pollution, for instance, and also in other countries, particularly you hear about China these days. So these kinds of improvements really matter. Depends what you compare it to. Taking an old coal plant offline and replacing with a natural gas plant is definitely an air quality win. But it's not an air quality win if you're comparing it to a new solar facility or a wind facility. So it always depends on what you compare it to. All right, those are some of the benefits. What are some of the potential interactions for people, both local and more regional? Right, there are interactions of on-site workers, clearly, the people who are engaged in that industrial activity. The compressor stations, the drilling and well completions while the oil and gas is being sort of prepared to start the pipeline. The holding ponds from which you might have volatile gases that can move into the atmosphere and then drift downwind for someone who's living nearby. And even in some cases, winter ozone formation. Hydrocarbons catalyze ozone formation under some conditions. So these are some of the things. Okay, so I want to look at leaks from oil and gas operations, how we can know more about them, how we can estimate what the total amount is, where they come from. This is a study that Adam Brandt did here at Stanford and many others. This came out last year. And I just want to show that these are sort of what we call upstream drilling and extraction activities to downstream activities. The example I'll talk about today is primarily in distribution lines in cities. And leakage, according to the EPA, is roughly equal from upstream activities and downstream activities. And it's important to note that methane is the #1 greenhouse gas under human activities in the United States. So in terms of a human source for greenhouse gases in the US, for methane, the oil and gas activity is the #1, and of course CO2 is #1 overall. All right, so downstream and upstream are about equal. So let's look upstream. Last week I was in the Bakken with a group with a helicopter and aircraft scanning, flying well pads. So last week we flew about 500 well pads. This is in North Dakota. We were asking a couple of questions. One was, what proportion of well pads leak? And how big are those leaks? Are they small and are they large? And how do we know? So we had a helicopter with an infrared camera to fly over these well pads. So you can see, using the camera to see in the infrared, where you can see the leaks that are not visible to the naked eye. All right? We had a small aircraft. Steve Conley's group from Boulder was there. When you see a big leak, you want to know what's the volume of gas that's moving to the atmosphere. So we can use the aircraft to fly back and forth across that plume. So look at the size of that plume and look at the concentration gradient from the site. So that gives you information about the emission, how much gas is leaving that source. These are just a few of the pictures. There's a lot of flaring that goes on in the Bakken. These are some tanks, some pump jacks, and then some water holding facilities. Okay, now one of the things we've done going back last year, this is work with Environmental Defense Fund, is to quantify these, to answer these kinds of questions. So let me give you an example from what you might see on one of these flights. This video isn't from the Bakken because I haven't had time to process these images last week. But let's run one, if this works. Okay, so this is a booster station. This, in fact, is in Texas. This was taken last fall. There are a couple of small leaks on this facility, so you're looking down on the operations. And then we'll switch now into infrared mode. So you're in the helicopter flying around. There are some small ones that you can see. It'll probably be hard to see in this room. Let's just watch it for a minute. You see tanks there. And there's the leak. Okay, so not visible to the naked eye, but visible in the infrared. So depending on where you are around the country, in different places, different plays, you might see a leak like that. Those rare in, 1 in hundreds of operations. Other places it might be as common as 1 in 10. All right, so we're interested in understanding different shale plays around the country, understanding what the predictive factors are for those kinds of leaks, and how to help fix them. That's an upstream example. Let me finish with a downstream example. So now we talked about how emissions in general seem to be about equal upstream associated with the extraction activities and about equal downstream associated with shunting or moving that natural gas around. So our group, working with a colleague, Nathan Phillips of Boston University, published the first studies where we map city leaks, publicly available maps. So we put a methane analyzer in a car. You see that analyzer here. It's a laser-based instrument, measures the methane concentration. We drove block by block across the city of Boston. That's about 800 road miles, about 1,500 road miles across Washington, D.C. Okay, what did we find? Well, here's Boston. Red is road miles driven, and the yellow peaks are leaks, individual leaks that are coming up out of the ground from the infrastructure. Okay, number one predictor of a leak in Boston, where we mapped over 3,000 of these, old cast iron piping. All right, so some of these pipes date back into the late 1800s. Some of them are unprotected steel. So it's really an infrastructure issue, not that different from our water mains, our bridges, and our roads in this country. How much is coming out of these in sum? Now that's really hard to do going from 3,000 sources and other sources in the city, biological sources and otherwise. So the way we chose to do it, this is work that was led by Catherine McCain, she's at Harvard, is we put sensors on top of the building in Boston. So rather than trying to scale up from individual leaks, we put instruments on the skyscrapers, on buildings in Boston, and instruments outside of the city, so that when the air blew in the city, you could start with fresh air, and then look at how the concentrations of different gases built up in the air over the city. And if the methane over the city is coming from natural gas infrastructure, you ought to see not just an increase in methane, but an increase in ethane as well. And you ought to see it in approximately the same ratio as it occurs in the pipeline. And that, in fact, is what we found. So here the blue line is the range, is the average of that relationship, methane to ethane. The red and black are what we mapped, and each of these is an observation period. So that you can see that not all of the natural gas, of the methane in the air of the city is coming from natural gas infrastructure, but almost all of it is. In winter it's about 90%, in summer it's about 60%, but the volume's about the same. In summer you've got other biological sources, landfills and wetlands and things like that. All right, so we have a pretty good sense of how much is coming into the air. The take-home message here, that Boston Metroplex was losing almost 3% of its natural gas to the air. That was 2.5 times more than the state inventory suggested it was or should be. Washington, D.C. was the next city we did. This is Capitol Hill, one of the oldest neighborhoods in Washington. You can see the leaks behind it. Here's an app the Washington Post did based on our data set. Here we've mapped over 6,000 or about 6,000 leaks across the city. Once again, old piping is the number one predictor. Okay, what can we do with this kind of information? Well, we can, for instance, identify the places where the highest concentrations are found and use those as places perhaps to start with some of the repairs. So it's not feasible to say we need to go fix all 6,000 leaks. That's not cost effective. So we need a cost effective way to prioritize where we do this based on sort of the size of the leak, safety considerations, and the cost. And then finally, this is a paper that was just released today. So we had 3 follow-up cities, Manhattan, Durham, North Carolina, and Cincinnati. All right, why those 3 cities? Well, in this study, we wanted to target cities with completed pipeline replacement programs. So we wanted to ask the question, how much of a difference do those programs make? Cincinnati and Durham have just completed pipeline replacement programs. They've gotten rid of all of those cast iron and unprotected steel pipes. Manhattan is decades behind, similar to Boston and Washington, D.C. So here's what we found, 90% fewer leaks or less in Cincinnati and Durham than in Manhattan and in Boston and Washington, D.C. the cities we had done previously. So these are just the maps for those cities. Durham here, Cincinnati here, and then Manhattan here. There are big chunks of Manhattan that we couldn't drive because the skyscrapers are so tall you can't get an accurate GPS position to mark the position of the leaks you see. Anyway, 10 times more leaks, tenfold fewer leaks in Durham and in the cities with the pipeline replacement programs. So these policies really, really make a huge difference. All right, these are some of the justifications for fixing these leaks, and I'll finish with this. Money, people pay, ratepayers pay for the natural gas that goes missing from these pipelines. So that's a couple $2 billion a year. Jobs, consumer safety. In rare, very rare instances, buildings do blow up. People are harmed, partly from old infrastructure and partly from human error. Hydrocarbons catalyze ozone formation, so there's an air quality justification. And then finally, greenhouse gas emissions and climate change. Methane is the number 2 greenhouse gas under human control. So thanks for listening. We have plenty of time for questions. And if you're interested in this kind of work, let me know. We do field work, but we also do policy-related work where we compare different policies in states based on what we see on the ground and try and understand who's doing a good job and try and promote, use information to promote good policy. Thanks for your time. Questions? Start in the front. So the question was about a movie called Gasland that filmed people who could light their water on fire. Sort of how credible is that? Some people, so I have seen people who can light their water on fire based on, as a result of stray gas contamination associated with oil and gas activities and drilling. Other people, though, have been able to light their water on fire for decades. So not every case of someone who can light their water on fire is related to human activities. So one of the things we've tried to do is to build relationships. I didn't talk about our water work, but build relationships that allows us to understand under what conditions high methane concentrations occur naturally and the other elements and other compounds that you see with them, and then compare that to the cases where otherwise you have someone with really pure water who all of a sudden has water that bubbles like champagne. So sometimes it's credible, sometimes it's not. Next. So the question is about upstream leaks. Do we notice differences based on the region where we are and by the operator? So we do under both cases. I guess a fair summary would be that the oil plays like the Permian, the Eagle Ford in Texas, the Bakken where I just was, where there's a lot of oil and condensate to be had, tend to have more methane leaks, partly because the methane's not as valuable, and partly because the focus is on other compounds. So it matters where you are, and we do see sometimes differences in operators where there are statistically significant relationships between operators who seem to be doing better than average and sometimes worse than average. No, I'm not going to tell you whose those are. Next. All right, so first question, the main question is there a difference with unconventional sources compared to conventionals? So there is. I think it's really important both for the leak side and the water side to think about not just how much is leaking out or not just how much water is being used, but how much energy you get back out. So for instance, hydraulic fracturing tends to be more water intensive, to use more water than conventional obviously, but you get a lot more energy back out. I mean, surprisingly on the water side, when you compare water use per unit of energy, hydraulically fractured natural gas is a little better than nuclear and coal, and a lot worse than wind and solar PV. So you really have to take into account how much energy you're getting back out. Same for the leak side. Yes, they tend to leak a little bit more, but you also get a lot of energy back out of them. And yes, there are regulations, new regulations, both at the state level and at the federal level that are being deployed. There was one back here. Okay, we'll go here. So the question was about the utilities and do they monitor their pipelines? They do. It tends to be much more human capital intensive to do it traditionally rather than just being able to use new instrumentation and drive a car around. So one of the things I didn't talk about today was that in some cases with high concentrations we got out of the car and tried to identify the source under the streets and looked under what conditions you find dangerous leaks as well. So the utilities are concerned particularly and appropriately about safety. You know, the grade 1, the class 1 leaks that where they end up on the news, but not necessarily about the large leaks. So a large leak can flow under a bridge into the atmosphere, that it's never going to be an explosion risk. That leak may not get fixed compared to a smaller leak next to a building that poses a direct safety risk. So the companies do know about it, but I think new technologies are allowing us to find these more quickly, and these kinds of technologies are being used now by companies like PG&E here in this area. Somebody can cut me off, Lee, when we're done. There's one here. So the fans are loud. Are there any other what being used? Fracking fluids being used besides water? I mean, there are. You can use with shallow hydraulic fracturing. There's some nitrogen fracturing that's done in coal bed methane extraction. You can use propane gels and other things, but there's nothing as abundant, dense, and cheap as water is. So all these other things are possible, with the exception of, with the nitrogen one that is being deployed now. But in terms of gels and other things, there's really no substitute yet for water. Maybe a follow-on point is can we do a better job of using brackish and poor quality water versus pure water? And the answer to that is yes, I think we can, and some companies are starting to do that. But the wastewater is really salty, far saltier than seawater, for instance, in some of these locations. So you got to dilute it no matter what you do. There's one back here. All right, we'll go here. I don't know. Okay, so I don't know if people can hear that in the back, but the question was really about a pretty vociferous debate that's gone on, in particular about coal versus natural gas, and how much greenhouse gas benefit is there for natural gas compared to some energy sources. So at the combustion stack level, at the power plant level, when you're burning it, natural gas is about 50% less CO2 intensive than burning coal is. So right off the bat, that's a win. I've already mentioned the air quality benefits, which are very, very real in terms of other pollution. The issue, though, is how much leakage occurs with natural gas extraction and how much methane leakage occurs with coal extraction, because that happens too. So some of this research that I've done, lots of other people's work around the country and around the world over the last 5 years or so has tried to tackle that question of what's the total leakage of methane, and is it possible that it's enough to offset that combustion benefit compared to things like coal? And my take on the literature on the last years of research is one that leakage is higher than the EPA and the state thinks it is, not so high that it offsets that 50% combustion completely. So taking an old coal plant offline and replacing it with a new natural gas plant is still an environmental win, in my opinion. It's not as much of an environmental win as replacing that coal plant with a gigawatt wind facility or a solar PV facility or something, which saves water and air. But we need, we have this sort of balanced energy portfolio, and coal is the most intensive pollution and water and otherwise fuel that we have. So the first question was about approval. Do we get approval to fly the helicopters? Well, so literally, you do not need approval to fly a helicopter. Now you can't fly 20 feet over an operation and create a safety scene, but you don't need approval. In some cases we did have approval, in some cases we didn't, for different reasons. So to get a really objective view, what you want is to be under normal conditions, right? So it's like telling someone, if you run a restaurant and I tell you, all right, I'm going to be there on Tuesday of next week to inspect your restaurant, I can still learn something from that inspection, but I'm not going to learn as much as if I just show up on your door and walk in, right? So in most circumstances, we want to try and get the realistic conditions. However, there have been conditions in the field where we've seen something that we felt was unsafe. We have actually called those operations to notify people. In general, folks know we're around anyway. I mean, it's pretty hard to keep things quiet. That's just the way the world works. You had a second question. I don't remember what it was, but
when you do call them and tell them, oh, we found this significantly, well, how do they respond? What's the relationship?
Yeah, I think it depends on what you find, and it depends how you say it, like everything in life. So, there have been times in my work over this, more on the water side than on the air side, that I've gotten pretty strong pushback from companies involved, and maybe maybe more surprising to people, strong pushback from some of the state regulatory agencies associated with it, because they don't like us to say we think there's a problem in a subset of cases when they've said there isn't a problem. So I think in general, the people who work for the companies want to do the right thing. I think in general they're interested in in better information. They don't always like to hear what we have to say, but I think engaging is better in general than not engaging. When you hold up those signs, Lee, they're backlit in that window, so I can't really see them. So, are we done? Thank you very much.